So this lecture is going to cover emission systems at a more owner-operator level. Boost your vocabulary or understanding of the emissions systems and of the smog program that we deal with in California. Make sure that you're aware of the programs that are out there and more familiar with the smog check program so that you can make better choices about where to smog your vehicle and what your options are. If you've lived in California long enough, you've realized that you're required to do a biannual smog on your vehicle. So every other year you're required to smog your car. And they give some exemptions to that if you buy a brand new car, then for the first 4 years you don't have to smog it on your gas vehicles. And then you're not due for your first biannual inspection until 8 years after that for your model year. So right now, the 2012 cars that were brand new in 2012, they're getting their first biannual inspection. So if you take the year of the car and add 8 to it, then they're due for their biannual inspection. So that window between a car that is 5 to 8 years old, they only require a smog if that person sells that car. And so they get an exemption from their biannual inspection for the first 8 years. They get an exemption from a change of ownership smog for the first 4 years. We're smogging gasoline vehicles from 1976 to current. In 2010, they brought in the diesel smog program where they're smogging diesel vehicles from 1998 to current. And so if you caught that, they haven't always smogged diesels, and in 2010 they started smogging diesels and they retroacted it back to 1998. And so they went backwards 12 years and started bringing in vehicles for a smog for the first time. And so the point that I want to make to you about that is that the California Vehicle Code book is a pretty thick book, and the laws that are on those books are the laws that are on those books. That people that had diesel vehicles back then said, well, I don't have to smog it, I can do whatever I want, right? Just like people that have a vehicle that's 1975 and older are like, well, I don't have to smog it, I can do whatever I want. Understand, the smog law is based off of a law that's called the Clean Air Act. And that Clean Air Act is what gives the jurisdiction, not jurisdiction, but it gives the legality. It's the law that brings about the smog program. And so based on that, they bring out the smog program, and we're having to smog cars because of this law. However, there's other laws on the books that if they choose to enforce those laws, then they can retroact that stuff back. And so I want to caution you in this sense that just because you're not required to smog that car, it doesn't necessarily mean that you get to do whatever you want to that car. You can gut all the emissions off of it and so forth. Because as we see in the example of the diesel, they can always retroact that back and hold up a law that's already on the books. For your information, some of the emissions components that we'll talk about, the laws that require them go back to the 60s. So I caution you in this sense that there's a lot of practical ways that you could find yourself in hot water, and I want you to be wise. For example, if you get pulled over on the street for speeding or for, not stopping at this stop sign or whatever, right? You probably don't want to smart off to the officer. You don't want to do that anyways, all right? I advise against that. If you think you're wrongly pulled over anything, that day is not the day to fight it. You shut your mouth and you wait and you fight it in court. You just shut up, take your ticket, fight it later. Don't fight it that day. Because one of the things I want to express to you, just to be a wise human being, California Vehicle Code's like that freaking thick. I guarantee you, for most of your vehicles, unless you're incredibly careful, there are other things on your car that you could get a ticket written for besides whatever that officer pulled you over for. And especially if it's your little hot rod, little classic car or something like that, and you know that's not the stock motor, and you know that that thing's not stock anymore, you really want to shut up and just take the ticket. Because if you happen to get an educated officer that knows some of those other laws, they can throw a lot more laws and write you a lot more fix-it tickets that you don't want to have to deal with. So be wise about that. The other one that I want to warn you about, at least, is just like they retroacted back and started smogging diesels, if you looked on the Air Resource Board website right now, you'll find that motorcycles are on there. They wanted to smog motorcycles at the same time that they started smogging diesels. The environmentalist kind of movement, if you will, is going after all of these polluting or emissions producing sources. And so I know friends of mine that have motorcycles and things, and they buy a new motorcycle and they want to gut the cat off of it, and they want to gut a lot of the emissions components off of this. And what I'm telling you is, you better save them. There were some of the diesel people that threw away $8,000 worth of exhaust equipment, and then when the smog program came in and started smogging those diesels, they had to buy it back new because they didn't have it anymore. So at the very least, if you are a motorcycle person and you're taking parts off of your motorcycle, you save those stock parts. Don't destroy them, don't mess them up. Make sure that you save them and store them away, because there may come a day that you have to put those back on that vehicle to be legal to smog this. So fair warning on that. We're going to cover a few more details of the smog program, and after we cover a little bit more about the different emission systems and components that are involved. So this is a really basic overview of some of the emissions components that are there. They're the exhaust that is generated from a car. We understand from what we've talked about with fuel systems that if we nail that air-fuel mixture perfectly, then we really don't have emissions coming out the tailpipe. We have CO2 and water that'll come out the tailpipe. But the reality is, in all the transient conditions of accelerating and decelerating and all the different air-fuel mixtures that computer is having to produce to move this car down the road, the ideal air-fuel mixture is a hard target to hit. And so vehicles do produce emissions, and we have a variety of different emissions components that are installed on a vehicle to clean up those emissions before they exit the tailpipe of the vehicle. And so the emission systems deal with the inefficiencies of our internal combustion engine. However, in modern times, this has become an incredibly efficient engine. And so the technology that is there and the monitoring systems that are there, it's a very efficient engine. And so we've got systems that are handling the different emission sources. So fuel by itself is a contributor to smog in our air. And so we've got a system that manages any fuel that evaporates from the tank, and it's called an evaporative emission system, or an EVAP system. And so fuel vapor is captured and not allowed to escape out into the air. We have an EGR valve, which an example of those looks like this. So this is one that is mechanical, that's vacuum operated, and this is one that's electronic, that is used to control NOx emissions. And we'll talk about how that is accomplished. But we've got a PCV system. A PCV system stands for positive crankcase ventilation, and it's PCV, all right? Some people screw it up, and I shouldn't even say what they say, but I will, but they'll call it PVC, but that is a type of plastic pipe. The rest of this with the exhaust, we've got some other major components such as a catalytic converter, which is another place that we combust fuel in the exhaust and break down the emissions that we care about, which are HCCO and NOx. Those are the ones that we're trying to control primarily on our gasoline engines. And then we've got a variety of sensors that are involved to monitor all of these different emission systems. And there's even some systems that are not listed on this, but this is what you would typically have on a modern vehicle. And some of your modern vehicles don't even have an EGR valve. They'll just have the evap system, catalytic converter, and monitoring sensors. So the exhaust on our cars is something that is a major source of the emissions that we deal with. And so some of what I want to loop into this is just a general knowledge of exhaust components as well, which is what this is, and then we're going to get straight into some of our emissions. And so we've got exhaust manifolds that typically from the factory will be cast iron, or sometimes they're steel manifolds. We'll have mufflers that are designed to quiet the sound of the exhaust, although a lot of people will modify them to make them louder. And mufflers can be changed on the smog program. You don't even have to have a muffler on your car to pass smog. So you could cut past your last emissions device, which would be your catalytic converter, and you could just have a straight pipe from there, and that's not going to be an issue as far as passing smog. This is not considered an emissions device. However, the exhaust manifolds can crack, and then that can cause us problems with setting codes for catalytic converters or oxygen sensor codes or things like that as we introduce fresh air. If you consider that the exhaust gets incredibly hot and then cools off, and gets incredibly hot and cools off. So we can have exhaust temps that'll go up 800 to 1,000 degrees just on a gas car. And so they're getting hot and cooling off. That causes this exhaust to flex as it heats up and cools down and heats up and cools down. That can fatigue that exhaust. Cast iron is brittle and it can crack. And when you have cracked exhaust, you can hear it. It's usually more noticeable in the mornings when that vehicle is cold. It'll sound kind of like a ticking kind of breathy sound, like a kind of sound. And so every time we have that exhaust stroke, and we're pressurizing the exhaust as we're forcing those exhaust gases out, it'll leak out of that. This is something that we watch for. It can turn your check engine light on. It's not necessarily something that often causes a performance problem other than if it affects an oxygen sensor and turns your check engine light on. But this is something that your car would fail smog for. Oftentimes stuff like this will happen because of broken exhaust manifold bolts. So if we have bolts that break, then it allows that part to flex even more. Some of this is just bad designs from engineering designs from the manufacturer that they've designed in weak points that would fatigue and crack. And so the noises that you hear, you can often see black soot around the areas that exhaust leak is. Where it is, and to be able to detect those, and it can cause check engine lights to come on and things like that. Broken studs are probably one of the leading causes for broken exhaust manifolds, as well as broken exhaust hangers. The exhaust hangers, they support the exhaust, the weight of all that exhaust, and as we break hangers, then bearing the weight of that exhaust, it lands on the remaining hangers as well as the exhaust manifold. And so it's something that when I'm underneath cars, I just kind of take a look and make sure that the hangers aren't broke. Some of you have seen cars like I have where their exhaust hangers are all broke and their exhaust is dragging or almost touching the ground as they're driving down the road. That ends up cracking exhaust manifolds from the strain of the weight of the rest of that exhaust. The exhaust manifolds are something that's common to be modified on cars, and so you get people that will put headers on their car. As part of the smog program, any aftermarket part that is not the stock component that vehicle came from the factory with has to be approved. And when that car was sold new, it went through a very vigorous testing regimen that's called the federal test procedures to prove that vehicle meets the emission standard for that model year and class of vehicle that was sold. And so anytime we modify a part on the car, whether that's headers like this, aftermarket air intake systems, intake manifolds, camshafts, cylinder heads, right? Any of that sort of stuff that touches an emissions component, fuel tanks, even auxiliary fuel tanks, anything that has any potential effect on emissions has to go through a process of recertifying that car through the Air Resource Board in order to be approved to be installed on any production car. When that part is approved, then it will be affixed, or it will come with a label that will show an executive order number and a part number that can be looked up on an Air Resource Board website. And so as part of the smog program, any aftermarket part, the most common of which would be headers and aftermarket air intake systems like filter and ducting. Those are the two most common things to see. We have to look those up as part of the smog to see if that's approved to be on this car. I want to share something with you about the header that's up on this screen. This header that's on the screen has a port right here for a oxygen sensor, and has another port down here. So these aftermarket parts companies like DC Headers, for example, could be the company that this header is. They will often make that header for an off-road application for non-street use and for street use. And they'll go ahead and get it approved if it's a common and popular car, a Civic or a Chevy pickup or a Dodge or whatever. Then in the process of producing a header for that engine platform, they run through and get it approved by the Air Resource Board. But that header will often be designed with two different uses: for a non-street use and a track application, and for a street use application. If you ever buy headers online or things like that, one of the things that you'll want to pay attention to is that if it is California approved. If it's a California approved part, then it would be legal to put on your car if it fits that application. One of the things that you will pick up on, or that I want you to pick up on if you're buying them on eBay or Craigslist or whatever, is that if you're looking at a header for your car to buy, if you're buying it used, and you see that it only has a port right here, this port only goes for this runner alone, I can tell you that will never be an approved header if it only has a port off of one runner. That will be a non-street use application, an off-road application only. That will never be a 50-state approved header, because the point of an oxygen sensor is to monitor the exhaust gas for all of the cylinders on that bank. So when this one was designed with the location there and a location here, when you install it on your car, you're supposed to use that one where it monitors and sees all the exhaust gas that's coming from that bank of cylinders, not just the one from the one runner. So if you were looking at one online and you noticed that it only had a port on the one runner, I can assure you that will not be a legal header. So moving on from there, we've got our hangers. So the hangers support the exhaust. If you ever find broken hangers, that's one of the things that leads to cracked exhaust manifolds and damage to the manifolds. Clamps is an acceptable way to put an exhaust together. They'll be clamped together like that or welded. Sometimes they bolt together with flanges and a gasket. But all of that stuff we will pay attention to and watch for just as maintenance level information. I've already mentioned in some of the previous lectures that PB Blaster is a good product for dealing with rusted bolts and stuff like that. The main preference that I have for PB Blaster is the way that it shoots like a squirt gun. There's probably a lot of chemicals out there that will work good as a penetrating oil to help deal with rust. But this one is one that is readily available and one that I would even recommend. So there's different colored smoke that can come from the exhaust system on a car, and the color of the smoke means something and tells us something about what type of fluid is being burned. And so when you see blue smoke like this will have like a blue tinge to it. We're burning oil. And so that can be burning oil from, it could be engine oil, could be transmission fluid, could be power steering fluid. And depending on the application and the age of the car, all three of those are possible, all right? for some applications, your more modern vehicles, blue smoke is almost impossible to get from power steering fluid or transmission fluid. They don't have devices that would connect that transmission to the engine, and the power steering systems are electronic, and so that's not an option. So if you saw blue smoke on a modern vehicle, it's pretty much has to be engine oil. But some of your older applications could burn tranny fluid, they could burn power steering fluid. There was a connection between the engine and a vacuum line between those components. But blue smoke, careless to what, is burning oil. All right, that's the connection to draw, is that blue smoke, if it's got a blue tint to it, it's some sort of oil. And so for engine oil, and the way you would know which one it is just pull the dipsticks, right? If you're seeing blue smoke from a car and you pull, then whichever fluid it's burning will be low, right? If the tranny fluid's low, then it's probably burning the tranny fluid on that old car. If the power steering's low, it's probably burning power steering fluid. If the engine oil's low, then it's burning engine oil. So that would be at least the logical way to go about it, and then track down the source from there. But if you get blue smoke under acceleration, then it's usually rings. If you get blue smoke on a cold startup, then most of the time it's valve stem seals from the car sitting overnight, and the valve stem seals are bad. You drain oil down into the combustion chamber door, and you first fire it up in the morning, it burns off some oil. If you have a turbocharged vehicle, then turbo seals can go bad, and we can burn oil that way too on a turbo or even a supercharger. So black smoke is going to be from cars that are over-fueling and running rich. The white smoke can be a variety of different things. Most commonly, we see it in the colder mornings where it's just steam, because we know water is a byproduct of combustion, and so it can be completely normal to have water dripping out of your exhaust, to see steam coming out of the exhaust. It does not fail smog for condensation or steam. However, if it's coolant, then that will also come out as steam if you had a blown head gasket or things like that. If it's a diesel engine, it can be raw diesel fuel that's being steamed out the tailpipe, or it could even be a leaky diesel exhaust fluid or DEF injector. And so these are some of our possibilities for the different colored smoke. White, water coolant, but it could be DEF or diesel. Black smoke is a rich air fuel mixture, a vehicle that is over fueling. And then blue smoke is burning oil or ATF, potentially power steering fluid. So now we're going to cover some of our major emissions control systems on here. The emissions that we're trying to control primarily are HCs or hydrocarbon emissions, CO, carbon monoxide, and NOx or oxides of nitrogen. And so those are the primary controlled emissions for a gasoline vehicle, and there's allowable amounts that are regulated by the government. I always have to throw this in there, that if I haven't said this before, if you pay attention to the automotive industry, there's often for whatever reason, in the public, there's a perception that the manufacturers are raising the prices on these cars to try to be more profitable. The reality is that everybody's in business to make a profit. They have to maintain a profit margin. My observation of what takes place in the industry is that cars get more expensive because of government regulations. The government regulations enforce and mandate a certain emission standard. They mandate a certain technology for safety, whether it's or emissions for tire pressure monitoring systems, or every car has to have airbags, every car has to have ABS and blah blah blah. They mandate certain emission standards, and to achieve those government regulations, the technology to support that makes these cars more expensive. And I'm reminded of that when I look at my statements that say that the allowable amounts are regulated by the government. And so it's not the big business manufacturer that is raising the price of these cars, it's them chasing the government regulations. And so blame the government for the cost of the car. Because we could make them a whole lot cheaper if it wasn't for the standards that they're putting in place, especially the fuel economy standards and emission standards. So these are some of the emissions components that we're going to cover in this that are used to control our HCCO and NOx. And most of these target a more specific category of emissions. So I want to give some definitions to the emissions that we're going to talk about first. So these definitions are the way, it's a functional way to understand what that emission is on a smog report or when you hear it talked about. So HCs or hydrocarbon emissions are raw fuel, any raw fuel. And so gasoline is a hydrocarbon emission, diesel, propane, ethanol, methanol, those are all hydrocarbon-based fuels. There's differing amounts of the amount of hydrogen and the amount of carbon, but at their base, they're a molecule that's composed of hydrogen and carbon. And so HCs is raw fuel. All of petroleum products are HC based. So the sources of this is either fuel comes straight out the tailpipe, which, understand this, if fuel went into the motor and left unchanged, then we didn't burn it, right? Thank you. That's what takes place if you have HCs come out the tailpipe, that fuel came into the motor and left unchanged, all right? So that should clue you in to the types of things that can cause HC emissions. Could low compression cause hydrocarbons? Yes, because if you can't compress it, you can't light it, right? Misfires of any sort cause hydrocarbon emissions, all right? So ignition system doesn't light it, low compression, lean misfires, all right? It also, another source of hydrocarbon emissions that it allows it to escape into the environment from the vehicle is if it evaporates in the tank and escapes out of our fuel tank. So the carbon monoxide, CO, considered a toxic, dangerous gas. That's why we would not run engines in an enclosed room indoors, things like that. CO, yes, is, you always hear like it's colorless and odorless, right? I just showed you a picture of black smoke coming out of a car. That was CO, all right? And so not all CO is colorless and odorless, and you can smell it. It smells like rotten eggs. I don't know if any of you, I'm sure all of you have driven behind an older car where you could smell their exhaust. You're smelling the CO. Now, we can see it, we can smell it. So it's not an entirely true statement to say like, well, it's colorless and odorless. No, when you can see it, it's black, right? I can smell it, it smells like rotten eggs, right? Now, the dangerous part about CO is that even when you can't see it and you can't smell it, it can still kill you. Which is why that statement has come around to be, is that it's not that it's always colorless and odorless, but the dangerous part about CO is that even when you can't see it or you can't smell it, it can still kill you. You only get CO from cars that are running rich. Now, quick little demonstration. In the motor, what comes in is HC emissions, all right, or they're not emissions, it's fuel, right? So this is fuel, all right? Then we have oxygen, and then there's nitrogen, all right? Then we burn it. So we separate our hydrogen, we separate our oxygen, our carbon, and then we add oxygen to this, right? H2O, CO2, all right? And that's what should come out the tailpipe. But when things are not perfect, then you'll get your end tube that would come out. That would be ideal, right? If we burn it and we make this. But if we add too much HCs, then we make H2O, and then you run out of oxygen, so then you make CO instead of CO2. So if you run out of oxygen because you added too much fuel, then you will make carbon monoxide because we're one less oxygen molecule there because we didn't have enough oxygen to go around with the carbon that was present in the combustion chamber. So then it makes CO, all right? So hopefully that makes sense on a chemistry level, how we get CO. If you add too much fuel, then there's too much hydrogen and carbon for the available amount of oxygen in the air, and so there's not enough oxygen to go around to make CO2, so you make CO instead. And so CO2 is considered complete combustion. CO is considered incomplete combustion because it didn't completely burn and make CO2, but it didn't completely burn because we ran out of oxygen from overfueling it, running the car on too rich a mixture. So the best way to understand CO as an emission from a diagnostic standpoint as a technician is that you only get CO when cars are running rich or being overfueled. Then we get to oxides of nitrogen. And this is a relatively simple one to explain, that there is nitrogen present in the air. About 76% of the air is nitrogen. So if combustion chamber temperatures exceed 2,500 degrees Fahrenheit, then nitrogen and oxygen begin to combine. And so that is what the source of NOx is. And so it's high combustion chamber temperatures. Now pressure and temperature are related, so it could be high cylinder pressure, right? High cylinder pressure, can timing affect that? Yes. Spark timing? Yes. Can compression ratios of how that engine is mechanically constructed affect that? Yes. And just the running condition of the vehicle, when vehicles are under load, they produce NOx. And so the crux of this is that this is just a picture of the skyline in Bakersfield, obviously. No, but we do have a lot of smog here in Bakersfield. But HCs and NOx in the presence of sunlight, all right, combust and react to produce ozone or smog. Ozone and smog are the same thing, all right? When they talk about it from like a medical standpoint, they'll typically refer to it as ozone. And ozone is the same ozone that's up in the atmosphere, but when it's down on ground level, we refer to it as smog. Smog is a made-up word that has to do with, that is smoky fog. Smoky fog, you put it together, it's the layman's term for ozone. Smoky fog is as a word as smog. You combine those two words. And so this is visible. So here's the deal. That's a picture of LA in the 70s. I have no problem admitting to you that I got into the smog program as a technician to make money, all right? The whole reason. I didn't go in to save the world or save the planet or any of that kind of stuff. That's not still my motivation. It's not. I came into the program because this is a good way to make money. People have to come back and see you every 2 years. Pretty kind of secure type of job and line of work to do. The government makes them come and see me whether they like it or not. So that's my motivation for getting into the smog program. However, I don't want to live in that world, right? This is modern day China. That's what their air looks like. That's LA in the 70s before the smog program came into being. I didn't live through those times or go and visit in LA back then, but I know people that have. The referee, smog referee that's here on campus, he grew up in LA, and he said there was some days down in LA that you couldn't see from one telephone pole to the next, and to breathe that air would burn your lungs, it hurt your lungs. So even though that's not my motivation, there's a level of this that is of the smog program that is certainly good for public health, all right? And so I don't want to live in that world. This is modern day LA. So better, right? Certainly better. That's actually the same camera view. So you can actually see this little tower right here and picture there that is that building right there. And so significantly better air because of the smog program and cleaning up the emissions on cars. So even though my motivation is to make a living for my family, there's certainly a benefit to the smog program because I don't want to live in that world right there. So there's a there's a significant relationship between the air-fuel mixture that we run our vehicles at and the emissions that come out the tailpipe. The air-fuel ratio that we run our vehicle at is not only ideal chemically for getting the most out of the energy that from burning this fuel, but it's also the compromise for the best emissions. The stoichiometric air-fuel ratio is not the best for power, right? The best for power is more like 12 to 1. The stoichiometric air-fuel ratio is not the best for fuel economy. The ideal air-fuel ratio for fuel economy is more like 16.5 to 17 to 1. All right? That would get us better fuel economy. However, anytime we move away from stoichiometric air-fuel ratio, we have a problem with other emissions. If we add less fuel and go leaner, although that would be better for fuel economy, that raises combustion chamber temperatures, and so you start to see NOx emissions increase. If we're adding less fuel, then obviously we would see HC and CO decrease. If we go richer than that, that is better for power, which sometimes, by the way, we do run this mixture, we do run that one for when we're trying to pass somebody on the freeway or something like that, or get on the freeway, then you're going to go to a rich air fuel mixture. But when you do, then if we're adding more fuel, then we would expect that HC and CO would increase. Adding more fuel actually absorbs heat and cools off the combustion chamber, and so then NOx decrease. However, the best for HC, CO, and NOx is going to be a stoichiometric air-fuel ratio. So, the sources of vehicle emissions come from different places. The majority obviously comes out the tailpipe. However, uncontrolled, about 20% of the emissions would come from fuel evaporating. Another 20% would come from crankcase vapors. So sorry, there's your fuel evaporating, there's your crankcase vapors. But the majority is going to come out from the tailpipe. However, all of these areas are controlled on a vehicle with emissions devices. We've talked about in labels the information that is on an emissions control label. I've tried to express to you that this is our most accurate place to get the year of the car and the engine size. The other information that is on there is stuff that we use when we smog a car. It tells you what emissions components are required to be on that car, and gives us information about that. There's also some tune-up specs and different things on there, whether a car is OBD2 certified or not. But as it relates to emissions, it gives us a list of the emissions components that are on there. So this car has a 3-way catalytic converter, has air-fuel ratio sensors, has heated oxygen sensors, and it's sequential fuel injected. So it gives us a list of some components that are there. Some of the stuff that's not on this is the fact that all cars are going to have a PCV system of some sort. All your gasoline vehicles are going to have an EVAP system of some sort. They don't need to list it, and they don't, because all of those vehicles have those emissions components. So, positive crankcase ventilation, PCV system is one of the first ones that I want to cover. So PCV, its job and what it does, it will control HC and CO, and it controls blow-by gases. Whatever combustion gases get by the rings and settle in the crankcase, they're not going to just escape out into the air. That would build pressure in the crankcase. Early and older cars just had a vent that kicked out blow-by gases out into the air. They called it a draft tube. That they just vented those out into the air. Modern vehicles are a sealed PCV system. We need a PCV system just functionally on a car. But what they do now is they ensure that PCV system is routed back into the motor to where those vapors from blow-by gases get burned. Without a PCV system, we would build too much pressure in the crankcase, and it would blow gaskets out and stuff like that. Because rings on the piston have a gap, and so there's always a space for blow-by gases to get by. Even on a perfectly good running engine, you're not completely sealed around the piston, and so we'll always get some blow-by gases past the rings. Obviously, when you're under hard acceleration and making more power, you have more blow-by gases than at idle. But the way that a PCV system is designed to work is that here's our crankcase area down below the piston and above the oil level. So below our piston, above our oil level is an airspace there. that when combustion gases escape past the rings, A, we don't want them in our oil, so we need a PCV system for that. If the system was sealed, we'd build pressure and have leaks everywhere. So it's been vented, and then it comes up to a little PCV valve that comes into the intake manifold. So manifold vacuum, we're down past the throttle plate. Manifold vacuum is going to pull and draw the air. Fresh air will typically come from an air intake duct over to the valve cover so that we can replace the blow-by gases that settled in the crankcase with fresh air. And so we get this circulation that fresh air comes in here as air is drawn out from the crankcase, and then that gets directed back into the motor to be burned. An evap system, one of the major components in an evap system is a charcoal canister. So a charcoal canister, I'm going to grab a couple over from here and get rid of this guy. So a charcoal canister is exactly what it sounds like. It does have activated charcoal in it that when we have vapors that are directed, that evaporate from the tank, they're sealed and directed over to the canister to be stored. And then however that vehicle is programmed or designed, they're going to ultimately direct those into the engine to be burned, which is a win-win, right? We don't want to waste fuel and just let it evaporate out in the air. If it gets directed into the engine and utilized to run the engine on to some degree, then that's beneficial to us. The canisters that you'll see, the older ones, were vented from the bottom. So they would collect it in charcoal, then you would have a line that came from the tank to here, collected in the canister in the activated charcoal that's in here, and they had a simple mechanical control valve that when you were cruising down the road, then they would open this up and and they would draw fresh air through this canister, and as the air pulled across the canister, it would bring fuel vapor with it, and then it could be burned. Your newer systems are checking to make sure that that system isn't leaking. They're pulling the tank into a vacuum or pressurizing the tank as an active test that computer will perform to make sure that the system isn't leaking. So your newer ones, the canisters are all sealed up, and then they're controlled electronically with a vent solenoid, which is the control to control the fresh air side, which your older ones were just vented all the time. The newer ones, so that they can check the system, they have a little solenoid that can control fresh air into the canister, and so that would connect to this side over here. Then they'll have an electronic purge solenoid, and then obviously even things like your fuel cap are designed to be able to seal off and make sure that there's no leaks. So there you got in your evap system your fuel tank, your lines, a fuel cap, a vent solenoid, a purge solenoid, and then one of the other devices that's there is a pressure sensor for when they check it. Now, older systems could not monitor the evap system for leaks, and so on the smog program, you should be aware that 95 and older vehicles, we pressurize their evap system with a machine as part of a smog to see if it leaks. The reason why I bring this up is that you can head yourself off from a failed smog if you know that when you put fuel in the car, you smell fuel after you get back to your house, or you see it dripping because your filler neck's leaking, or anything like that. You should get that fixed before you smog the car, because if not, if you have a 95 and older vehicle, when we pressurize that evap system, it's going to fail. So be aware of that. That's an easy one to head off, that you could save your money on a failed smog if you already know your tank has a leak somewhere. The evap system works like this. Older systems, like is what's demonstrated in this picture, but they've got their tank. In yellow would be our vapor space. That gets directed over to a canister, and then they're controlling when they purge that into the motor to burn the fuel vapor that's collected in that canister. An EGR system, EGR stands for exhaust gas recirculation. So this is the way that system works. It controls NOx by directing exhaust gas back into the motor. And some of you guys are like, that sounds like a freaking genius idea. It is, all right, it is. The way that it works is that if they, we had a normally running engine and we directed 10% exhaust gas into the airstream, all right, then when that blend of air fuel mixture and exhaust gas gets into the combustion chamber and it gets sealed off because our valves are closed, we compress that and we light it. Since 10% of what trapped in the cylinder we can't make power from because there's no oxygen in it, it's exhaust gas, it's already been burned, then I have a smaller fire. If I have a smaller fire because I have 10% of exhaust gas that can't make power, then I have 10% smaller fire, then that makes less heat. If I make less heat, since NOx is caused by combustion chamber temperatures exceeding 2,500 degrees Fahrenheit, if I have a smaller fire, I make less heat. If I make less heat, I make less NOx. And some of you are drawing the obvious conclusion to say, well, don't you also make less power? Yes, all right? So one of the things I'll assure you, though, little Ricky racers that are out there, they will not turn this EGR valve on in a scenario where we need power. If you're trying to pass somebody on the freeway or you map your throttle to the floor to where your throttle's over 75%, that's considered a wide open throttle signal to any computer. So if you're accelerating under hard acceleration, one of the things they will not do is turn the EGR valve on, because the priority at that point is to make power. And so the early systems, some of you may be old enough to remember when they brought in EGR valves in the 70s, and it noticeably gutted the power off of these vehicles because they weren't good at, they hadn't fine-tuned when they were going to activate that EGR system. So it did hurt the power on the engines as they first brought in these emissions components in the 70s. But then since that time, they fine-tune the control of systems like the EGR to where they don't bring it into play in a scenario that would affect the power of the engine in a noticeable way. So they'll turn the EGR valve on at cruise, under light acceleration, things like that. They're not going to turn it on in a scenario where we need power because, and even for just the safety factor, right? When we need all the power that engine can make sometimes. And so they're not going to turn the EGR valve on in a place that is going to affect the power output of that engine.